with the chapter 2, the probability of combined events. What will we learn in this chapter? What sample space diagrams and tree diagrams are, how to calculate the probability of combined events using sample space diagrams and tree diagrams, how to use the addition law of probability to solve problems involving mutually exclusive events, and how to use the multiplication law of probability to solve problems involving independent events, why probability has useful applications in real life. Now, start with a definition of sample space. What is sample space? In set language, a sample space is the set of all the possible outcomes of a probability event, i.e., it is a universal set in the set language. The total number of outcomes is the total number of elements in S and denoted by N of S. And the sample space is denoted by S. So what is meant by the word probability, we will see. But first we will see few definitions before discussing the probability. It is an event. The subset of the sample space is called an event, and it is denoted by E. The number of favorable outcomes is the number of elements in the set E and is denoted by N of E. What is complement of an event? Complement of an event is denoted by E prime, and it is the set of elements in the universal set which are not the elements of E. Since we have discussed the different definitions, sample space, event, complement of an event, now it's time to apply those definitions through a real life example. So consider a probability event in which a fair die is rolled. Since every number from 1 to 6 is a possible outcome of the experiment, so the sample space is equals to S equals to 1, 2, 3, 4, 5, and 6. This is a way
to
to
write
write
down
down. This is a way to write down the sample space in the set notation. And since in set language, the total number of possible outcome is the total number of elements in S and is denoted by N of S. Therefore, the N of S will be equals to 6. Suppose E is the event that the number shown on the die is the multiple of 3. So we will write it in a set builder notation is like E is equals to X such that X is a multiple of 3. Since the multiples of 3 in the sample space S are 3 and 6, so the favorable outcomes are 3 and 6, and the event E can be written as E is equals to 3 and 6. And we have learned that E is a subset of the sample space S. The number of favorable outcomes is the number of elements in the set E. So, for example, the N of E will be equals to 2. Now the set E prime, the complement of the event will be like this: 1, 2, 4, and 5. The remaining elements that left in the set S. Now let's see what does the event E prime represents. And the n of E prime is equals to 4. Now we will draw a Venn diagram to see the event E prime represents what. So here we have a Venn diagram where this rectangle is the sample space S, and the circle shows the event E inside the sample space, having the elements 3 and 6. And now we will write down the remaining elements, excluding the elements of the event, and those are 1, 2, 4, and 5. So this is the Venn diagram representation for the sample space, event, and the complement of the event. Now it's time to learn that what is probability. The probability is used to describe how likely or unlikely it is that something will happen. Something is any experiment that we can consider. And the probability always lies between 0 and 1. The probability of that any event occurs or not will be denoted by P of E. And this P of E is always lies between 0 and 1. 0 means impossible event. 0%. 1 means certain event. 100% probability. And if we have any value between 0 and 1, say 1 over 2, 0.25, or 25%, then this event is as likely and as unlikely. If we move towards the 0, then our event will be more likely to occur, more unlikely to occur. And if we take the value between 1 over 2 and 1, or our value is closer to 1, then our experiment will be more likely to occur. Now we will learn the formula of the probability of an event. Here we have all the outcomes equally likely. So there is no unlikely outcomes. All the outcomes are equal and likely. Now the formula to find out the probability of any event is probability P of E equals to number of elements in E over number of elements in S. Number of elements in E is denoted by N of E, and the number of elements in S will be denoted by N of S. So the formula will become P of E equals to N of E over N of S. Since we have discussed a example of a fair die is rolled, so the N of E was 2 and N of S was 6. So P of E will be equals to 2 over 6. First we'll write down the formula. The formula was N of E over N of S, and this will be equals to 2 over 6, and this will gives us 1 over 3. So P of E, the probability of an event, is equals to 1 over 3. So the probability of an event to be a multiple of 3 will be 1 over 3. If we see it here, now if we want to find out the probability of an event that the number on the die is not a multiple of 3, so that will be find out by using the relation P of E prime equals to 1 minus P of E. So in our case, this will be 1 minus 1 over 3, and it will gives us 2 over 3. So P of E prime will be 2 over 3. P of E plus P of E prime must be equals to 1. Now we will discuss the sample space diagram. The possible outcomes for rolling a fair die are 1, 2, 3, 4, 5, and 6, and we have write the sample space as in our discussed example 1, 2, 3, 4, 5, and 6 when a fair die is rolled. But how do we list the possible outcomes for rolling 2 fair dice? If we have 2 fair dice, what will be the sample space? Let's think. So we can represent a possible outcome by using an ordered pair. So here we will use the ordered pairs, e.g. 2, 3. 2, 3 means the first die shows a 2 and the second die shows a 3. What does the outcome 3 2 means? Is it the same as the outcome 2, 3? Let's think. But the answer is no. So first we will write down the sample space for the experiment where the 2 fair dice are rolled. So the sample space in our case will be 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Now we have 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and the last one is 6, 6. So this is our required sample space. What the ellipsis represents? It is not clear that the outcome after 1, 6 is 1, 7 or 2, 1. And it is not clear that outcome after 1, 6 is 2, 1 and not 1, 7. Hence, we need to represent the sample space differently. We have one way to show this by drawing a sample space diagram to represent the sample space for 2 rolling dice. So for this, we will draw a sample space diagram here. Here we will draw 2 axes, one vertical line and one horizontal line. This line shows the number when the first dice is rolled, and this one is for second dice. For second die. Now we will put the dots for one order pair, for each order pair. For 1, 1, we put 1 dot. For 1, 2, we put another dot. For 1, 3, we put another dot. For 1, 4, we put another dot. For 1, 5, here one another dot, and for 1, 6, here we have one another dot. So this dot shows 1, 1 ordered pair, this shows 1, 2 ordered pair, this shows 1, 3 ordered pair, this shows 1, 5, and this shows 1, 6. Similarly, we will put the dots in the sample space diagram.
From the above sample space diagram, we observe that the total number of possible outcomes is 6 times 6, which is equals to 36. The size or the measure of the sample space is 36. We can calculate the probability of combined events using a sample space diagram, as we shown in the figure. So now we will see what is the sample space diagram is. A sample space diagram is used to represent a sample space diagram is used to represent the sample space of two-stage probability experiment. where each component has where each outcome has two components. So here we have learned one method to find out the probability of combined events, and that is sample space diagram. Now we will see what is a tree diagram. A tree diagram is used to represent the sample space for a multi-stage probability experiment where each outcome has at least two components. And by convention, we draw a tree diagram horizontally from left to right. So first, as we have discussed the sample space diagram, so the sample space diagram for tossing two fair coins can be represented by a sample space diagram just like this. But first we will see the sample space for tossing the fair coin, that is head and tail. Now the sample space diagram for tossing two fair coins will be represented by a sample space diagram like this, head and tail, head and tail. This is for first coin and this is for second coin. And now we will draw the dots. This dot shows outcome HH. This shows outcome HT. This shows TH and this outcome shows TT. So let's think, if we want to toss three fair coins, then how will be the sample space represented? So let's think. To solve this problem, we will study tree diagram. Since it is difficult to draw a three-dimensional sample space diagram, so we have to use a different type of diagram called a tree diagram to represent the sample space. Now we will see the following steps to how to construct a tree diagram. So for this, when the first coin is tossed, there are two possible outcomes, head and tail. So we start with the point and draw two branches, H and T. So we indicate the first coin on the top of two branches. Now the second coin is then tossed regardless of outcome of the first toss. So the second coin would also yield either a head or a tail. Thus we draw two branches after the head and tail from the first toss as shown. There are a total of 2 times 2 equals to 4 branches. There are 4 possible outcomes at this stage. So we indicate the second coin on the top of the 4 branches. Now the third coin could also yield two outcomes when the first two outcomes are HH, HT, TH, or TT. Thus we obtain the tree diagram as shown. We observe that there are a total of 2 times 2 times 2 times 8 branches. The total number of possible outcomes is 8. So the branch highlighted in red will shows the outcome HH, and the branch highlighted in black will shows the outcome THT. Now we have the first question of the exercise 2A. List the sample space of each of the following probability experiments. In the part A, we have a fair 12-sided die numbered from 1 to 12 is rolled. So, in the part A, let S be the sample space. Since we know that the sample space is represented by S, so for the part A, the sample space will be equals to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Since when a fair 12-sided die numbered is rolled, so the outcomes of the sample space will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now for part B, a fair coin is tossed. When a fair coin is tossed, then we have two outcomes. So the set S will be equals to head, tail. Now for part C, a ball is drawn randomly from a bag containing 4 black balls and 2 white balls, where the balls are identical except for their color. Since we have 4 black balls and 2 white balls, so the sample space for part C will be like we will denote 4 balls by B1, B2, B3, and B4 respectively, and the 2 white balls will be denoted by W1 and W2. So these are the sample space elements for the part C. Now in the part D, we have to choose a letter at random from the word students. So since we can see that in in the word students, we have two S and two T. So we will call the first S S1 and the first T T1. Then we have U, then we have D, then we have E and N, and the second T will be denoted by T2, and the second S will be denoted by S2. So these are the outcomes for the sample space to choose a letter at random from the word students.